IME 300 class. This is Cash Erickson, as well as Mathias and Nick, presenting on binder jetting, a 3D additive manufacturing process that is currently revolutionizing part of the industry. So, what is binder jetting? Binder jetting is an additive manufacturing process in which a liquid binding agent is selectively deposited into a thin layer of powder particles.
So basically, binder jetting is likened to 2D printing as we currently know it. Think about any paper printers that we know now. Essentially, you can replace the ink on those printers with, in this case, the binding agent or glue in this printer. And doing that over a number of layers results in the end product. And then there's many different kinds of particles and powder that you can use, materials in this case. Sand, metal, ceramic composites, all good options. They all have different use cases, and of course they are, the industry is continuing to try to expand the types of materials that can be used for this process. So going into a bit of the history of the creation of binder jetting, binder jetting is a relatively new manufacturing process in the additive space. Originally created by a professor at MIT, Emanuel Sachs. He worked in the mechanical engineering department and was specifically trying to take 2D printing into the third dimension. And so that's why we're left right now in the current state of binder jetting with the process of applying binder to different layers, because it's inspired by Emanuel Sachs was inspired by the 2D printing that was used and has been used for years and years. And this is where the current state of this technology exists.
So, how does binder jetting work? Imagine a 2D printer, but it's doing multiple layers on that piece of paper. And every time it completes a layer of paper, a second layer of paper is added on and more ink is added. But in this case, a print head is selectively depositing a liquid binding agent onto each layer of powder particles, much like the size of sand particles. So very similar to printing on paper. It has similar speed and similar types of printing. How does it differ from other additive manufacturing techniques? So first off, if we were to compare it to the printers we have here at Kettering, it is much more capable to produce a high volume output due to the fast printing speeds and large bed. As we see in the bottom left, it can print many pieces all at once, as compared to the ones we have at Kettering would take a very long time to print every single or high volume. And as compared to other 3D printed manufacturing techniques, much like the ones we have at Kettering, it is most similar to paper printing, as others are not. Now watch a video on binder jetting.
Binder jetting. The 3D printing process, binder jetting, got its name from the binder, a glue that is applied by the print head during the printing process. After the start of the print job, the 3D print happens in two main steps. In the first step, the molding material is applied by the recoater. Layer by layer, the recoater applies molding material on the build area. With high precision, placing two grains the size of a sand grain exactly above each other. In the second step, the printhead applies liquid binder. The high-precision printhead allows the binder material to connect every single grain of the molding material completely, grain to grain. These two production steps are repeated. Again and again. And again and again, until the desired object is built layer by layer. After the printing process is completed, the loose molding material is removed. The printed parts can be extracted, and no matter how complex they are, finished during an easy post-process. Binder jetting.
And so now we're going to go into a case study from that same company, X1, who is a current leader in the binder jetting additive manufacturing technology space. And we're going to look at a case study where they worked with a company called Xylem. And Xylem is a manufacturer of water pumps and treaters. They do anything from essentially large-scale industrial pumps, treatment, to even very small-scale home use appliances, essentially. So one of their key products that X1 helped Xylem to reimagine how they manufacture and produce is their impeller cores. And essentially these impellers are crucial to water pumps and treaters as they help to propel the water in whatever way and direction that the machine needs. And so if we look at how Xylem used to manufacture the impeller cores, one batch, which would be anywhere from 20 to 30 impellers, would take about 7 days to produce. And essentially in this process, the impellers would be casted, and then each impeller would be divided into 4 sections. And so each of these 4 sections would be casted, and then they would be glued together, and that would create the end product impeller, similar to what we see in the bottom right. However, the bottom right is an example of the impeller made with binder jetting, and essentially how the binder jetting improved the process of creating these impeller cores is one batch of 20 to 30 impellers went from taking 7 days to produce all the way down to 2 days. And that was it's incredibly substantial change, and not only this, but also improved the parts that were made. So rather than being produced in 4 separate parts and then being assembled together, they're now produced in one single part, improving the structure and simplicity of the manufacturing process. Not only this, but the impellers now have an improved surface finish, which is important when considering the use case of these impellers in these water pumps and treaters. That's due to the fineness of the particles that's used for creating the impellers in the process, as well as just the general precision of binder jetting machines. And finally, one of the biggest changes made to the manufacturing process is now it is significantly easier to make changes to parts to these impeller cores, whereas in a traditional manufacturing process they would have to go through the process of creating all new cores and molds. The whole process would be incredibly strenuous in comparison to binder jetting, where you're essentially updating an STL file, changing settings in their slicer, and potentially reconsidering materials used. So, as you can see, this real world study certainly shows the application which binder jetting can be used in real life, and it's currently revolutionizing the industry of manufacturing and will continue to do so for the coming years.
So now on to the pros and cons of binder jetting. Starting off with the pros, it's faster and more cost effective than, say, traditional 3D printing ways. A benefit is that there are no supports needed, so it makes it very simple when cleaning it up at the end. And as you saw in that video, when he takes it out of the sand, all he had to do was blow the sand off. He didn't have to break off like sticks or something similar to that from the part. You can produce high volume. You can like many at a time, and they can be made with highly precise dimensions, which can be very crucial, depending on what it's being used for. And then the cons, the metal part durability isn't quite so good. It doesn't use heat when manufacturing the parts, so the metal isn't quite as strong as it would be otherwise. Seeing as how it is just tiny little fragments of metal basically being glued together instead of, say, like welding, where it's added together by extreme heat. And that's also very similar with the brittle parts, with it just being little fragments glued together. They can easily be broken apart. A big downside is the material choices that you can use with binder jetting, seeing as how it's just there's a smaller range of materials that you can use, which can lead to some downsides. And it cannot do small detailed parts. So let's say you're making some little tiny model, it won't be quite as detailed, whereas some other 3D processes could do that. Now, on the current status of how it's being used. Prototypes, it's very convenient how it can make multiple of them with very accurate dimensions, which is very nice for prototypes, seeing as how you can either break them in testing or other things. But it keeps it nice and cheap so you don't break the bank. Then you go on to aerospace components, just nice little thing. Cores and molds can be very nice because you don't want to spend too much money or something like that, but you also can get very accurate dimensions with that, causing the parts that come out of those to be even better. Tooling, it can also do tooling, casting, patterns, jewelry, all a lot cheaper than usual. And decorative objects, you can mass produce them and sell them and make even more money. I'm going to go on implications first. So companies like HP down in the bottom corner that are like working on more of 2D printing technologies, they're kind of racing and to build on this technology. Because they're already in the it's very similar, so it's nice. Scaling this process will dramatically improve quality and cost over time, like we saw in the case study that was mentioned earlier. And we go on to the conclusion. It's a promising additive manufacturing process with the potential to revolutionize production processes. It is a rapid, cost-effective creation of complex structures, and it is a very competitive option moving forward in the additive manufacturing world. And these are resources.